Hello students, in the today's class we are going to talk about the principle of extraction of metals. In the metallurgy lesson, the principle of extraction of metals. Which means what are the various techniques used in the isolation of metals from their ores. What are the metal treatments? What are the various steps involved in this that we are going to talk. Meanwhile, you know that what is called ore and what is called mineral. The mineral is the impure form of metal collectively known as a mineral. The mineral is the impure form of metal part which is available on earth crust. And what is called ore? The mineral from which metal is profitably and economically extracted in the quickest manner. So if you consider the best example, aluminium, bauxite is the mineral from which aluminium can be extracted, separated out easily, and hence bauxite is the ore of aluminium. Aluminium can have bauxite as its ore because from which the metal is quickly, profitably and easily extracted. And metallurgical treatments can have various steps. The first and important step will be the concentration of ore. How various ores are concentrated. Impure form of metal along with various types of impurities are taken from the earth crust, and from which how to enrich the percentage of metal and how to remove unwanted impurities in the primary stage. That is nothing but the concentration of ore. These are the various steps involved. One method of concentrating ore is gravity separation method. This gravity separation method is also called as hydraulic wash. Okay. And gravity separation method is highly useful for concentrating ores like these are the important ores. Fe2O3, which is called as hematite, and the ore of tin called tin stone having this formula SnO2, etc. Where in the process ore is washed with stream of running water. So while washing the ore with a stream of running water, the lighter impurities are washed out. What are called lighter impurities? The lighter and lightest impurities are called gangue. Simply, they are all washed out in this particular procedure. So this is the important part of concentration, the step of concentration, the method of concentration called gravity separation method, where particularly various oxides including Fe2O3, SnO2, and this method is also suitable for concentrating the native ore. What is called a native ore? Native ore means the ore which is available in the native state. For example, gold, it is in free state, native state. It is not going to combine with any other metal. The metallic impurities are not available in the gold ore, and hence it is called native ore. So the gold ore can be concentrated by this particular procedure called gravity separation process. And the next method will be the other one. Is froth flotation process. I'll tell you what's called froth flotation process. In the froth flotation process, in particular, ore is mixed up with suitable vegetable oil like pine oil, and it is to be thoroughly agitated by sending the air into that so that the froths are formed, which means the bubbles, the froth are formed. The froth will wash out the unwanted things as well as which collects certain metallic part. So the metal sulfides can be removed along with the froth. For example, if you take ZNS, what is it? It is nothing but zinc blend. And PBS, it is nothing but galena. These type of ores, in particular sulfide ores, are concentrated by this method. So it's an exclusive method to concentrate sulfide ore. These are the various sulfide ores, zinc sulfide, PBS. Washing the ore with suitable vegetable oil, and after mixing them, you should send air into the composite, and on thorough mixing, on agitation, froths are formed. The froth may take up the sulfide like ZNS and PBS, and unwanted things may be retained in the vessel itself. This concentration process called as froth flotation process. The metallic part is wetted with suitable vegetable oil. And here we must have an important note. Sometime if you take the ore like galena, PBS, certain percentage of ZNS may be there along with this. So how to remove ZNS from this? While doing this froth flotation process, in order to remove the ZNS present in the galena, we can add sodium cyanide into this the sodium cyanide added. So if you find ZnS along with the PBS, this ZnS can be removed by adding sodium cyanide, which can depresses the flotation property of ZnS just by forming the complex compound. You just see ZnS on treatment with NaCN, that is going to make a complex compound like this, Na2 ZnCN4. It's a complex compound made by that, and sulfur is removed as sodium sulfide. So this is the complex compound responsible for depressing the flotation property of ZnS, so that we can avoid ZnS from our ore called galena. So this is also happening there in the fourth flotation process, and followed by leaching, the next one. Leaching, which is having different category. These are the leaching procedures we should focus. One will be the cyanide leaching. Okay. Leaching is almost equivalent to bleaching. Bleaching the ore. Metallic ore should be bleached with suitable substances. First, we are going to talk about cyanide leaching. These are the power points to be recollected about the cyanide leaching. And you just know that in the cyanide leaching, it is applicable for the metals like gold and silver. In particular, if you take the gold, this on leaching with the cyanide, the dilute solution of sodium cyanide is used along with the gold, so that it can be converted into a complex compound. An unwanted thing, the gangue, the waste, lighter impurities, which are insoluble and they can be separated from the composite, so that we can remove the gold in the form of complex when it is treated with the sodium cyanide. The gangue is reminding that it's an insoluble portion, and along with the gangue we may have some other impurities like aluminum silicate. These are all present in the mixture itself because they are not soluble. So how the gold is forming complex compound? Yes, when you take sodium cyanide solution, solution means it should have excess of water in presence of oxygen. So gold is in the form of solid, and cyanide, it's a solution, aqueous, water, liquid, and oxygen is gas. While mixing these things together, you can have AuCN twice. It carries minus and OH minus aqueous. It is also aqueous, which means these are remaining in the solution and other things are deposited there as insoluble waste, including the gangue and aluminum silicate. And in order to balance this particular equation, we should take 8 times Cn, which means it is to be multiplied by 4, so 4 times Au, and H2O must be 2 times, and we are going to write 4 times OH. Okay, and this is the balance equation. In order cyanide leaching can be employed for silver also. So in place of gold, we can take the silver Ag in the form of solid that on action with the cyanide solution aqueous, having enough of water and oxygen in the form of gas. We will be getting a cyanide complex as follows, along with that OH minus. So this is the procedure when the silver is leached with the help of cyanide. In particular, the sodium cyanide solution is used up. So silver is recovered and other impurities are insoluble, that remains there. And in order to balance the equation, we can use the same idea. 4 times, this is going to be 8, and 2 times, here we will be having 4 times, 4 times. So both silver and gold can be leached like this. After leaching with the sodium cyanide, how to recover the metals from the complex compound? For that, we are going to use zinc, because zinc is more reactive than these two metals, namely Au and then Ag. So zinc is highly helpful to recover the metal from the complex. You just see Zn on reaction with one of the complex compound AuCN twice, which carries minus, RO cyanide, and it is in the form of aqueous, and Zn is in the form of solid, so that Au can be replaced by Zn. We will be having Zn Cn 4 times. It carries 2 minus, and the gold is separated. And this is what is happening in the leaching procedure. You see, the coordination number of gold is 2. It makes 2 coordination bonds, but zinc is making 4 coordination bonds. That's the difference. Okay. And this equation can be balanced by writing 2 times, 2 times. It gets balanced. Even the silver complex can be treated with zinc so that the silver can be recovered from the complex compound. So this is the procedure called as cyanide leaching. Just keep it in your mind. The metals like silver and gold can be leached with sodium cyanide solution. So this is the method based on the solubility of ore in suitable solvent. So here, which will be getting dissolved in sodium cyanide? Silver and gold are getting dissolved. Other things are not dissolved in that, and they are remaining as solid mass in the mixture itself. So this is the procedure called as cyanide leaching. And we are passing on to the next one. It is called ammonia leaching, which means ammonia bleaching. Here also certain metals are soluble in ammonia. Just by treating them with aqueous ammonia under pressure, ammonia can dissolve certain metallic part and forming the complex compound. For example, you consider the metal like nickel and copper, cobalt. Take metals like this and treat these things with aqueous solution of ammonia. NH3 under the pressure so that you can get the soluble complexes. These are the complexes we can have. Nickel can able to make a complex substance like this, NH3 6 times, and it is carrying 2 plus because it's a neutral ligand. The oxidation state of nickel is +2. Similarly, the copper can able to form CuNH3 4 times. It is going to carry 2 plus because the charge carried by the copper is 2 plus. And cobalt can able to make CONH3, okay, 5 times, and H2O, 2 different ligand. It carries 3 plus because the charge carried by the cobalt will be 3 plus. So these are the various complex compounds which are formed when these metals are leached with ammonia and they are forming the complex compound. And unwanted things are left behind. What are all the insoluble things? So these are all getting dissolved in ammonia, the metal part. And the insoluble part may have certain gang which is not dissolved in ammonia, and we can have iron oxides like Fe2O3 and hydroxide like FeOH twice, something like that, and aluminum silicate. These are all available, but they are not getting dissolved. So this is a method called as ammonia leaching. Simply while leaching with aqueous ammonia, the metal part is getting dissolved in ammonia, thereby they are forming complex compound with ammonia. And other procedure is alkali leaching. What is called alkali leaching? This is what is known as alkali leaching. For certain metals, this procedure can be used up. So these are the suitable metals, aluminium in particular. It is having the ore called bauxite ore. It can be leached with the solution of sodium hydroxide. You see Al2O3, the bauxite, on treatment with the sodium hydroxide solution, NaOH. Solution means it should have enough of water so that it is forming the complex compound as follows: NaAlOH 4 times aqueous. It is getting dissolved. Okay. After dissolving that in the solution of sodium hydroxide, it is solid, it is aqueous, it is in the form of liquid. In order to write the balance equation, I am writing 2 times, 3 times, and 2 times is a take. So the complex compound is soluble and other substances, impurities are kept intact and they are not interfering with the sodium hydroxide, so that we can separate out them. After getting this complex compound NaAlOH 4 times, how to recover the ore from that? For that purpose, it is to be treated with carbon dioxide. While treatment with the carbon dioxide, we can get back Al2O3, XH2O. The O is reobtained here, and we will be having sodium bicarbonate NaHCO3 aqueous. And for writing the balance equation, we can take 2 times and 2 times. So all metals cannot be leached by this particular procedure. The active metal like aluminium can be leached with the help of alkali. Alkali means the solution of sodium hydroxide. It's making a complex compound like this. And other will be the other procedure is acid leaching. Alkali leaching followed by acid leaching. This acid leaching is useful for the ores like ZnS, zinc blend, the major ore of Zn, and PbS, galena, the major ore of lead. These are all concentrated and they are leached with the help of acid leaching procedure. You just see ZnS on treatment with the acid H2SO4, the solution of sulfuric acid, along with oxygen. It can able to make ZnSO4. It gets dissolved and sulfur is separated out, and that forms water also. And to get the balance equation, almost these are all multiplied by 2. Okay. Except oxygen. Oxygen is in the form of gas. So this part is getting dissolved in acid and other things are left behind. All other things, the insoluble sulfides are converted into insoluble ZnS is converted into soluble ZnSO4. Okay, and other things are left there. Which part is left? All other impurities are left behind. Only ZnSO4 is dissolved in acid, and hence it is called as acid leaching procedure. So in all these leaching procedures or methods, we can recover the metal from the impurities. Okay. And after this, we are going to learn about magnetic separation process. What is called the magnetic separation process? The magnetic separation means the metal part which are attracted by the magnet can be separated from the non-magnetic part, the non-magnetic impurities which are present along with this. So the best example is wolframite. Okay, wolframite impurity, which is magnetic in nature, which is present in the tin stone. So sometimes it can have the magnetic character. So how to remove this magnetic wolframite impurity from the tin stone? Just by having the magnetic separation method, if you pass the ore on this conveyor, okay, the moving belt, this wheel may be a magnetic wheel. So while we pass the ore through the conveyor belt, the metallic impurity, which means mainly the magnetic impurity, are attracted by this, and non-magnetic substances are not attracted by this, so that we can separate out these two. In one vessel we can collect magnetic ore, and in other vessel we can collect non-magnetic ore. So it's a very simple procedure. Wolframite is having the magnetic character in the tin stone. Such kind of ore is passed through the conveyor belt like this. In one end we can have a magnetic wheel. The magnetic wheel is attracting the magnetic ore. The non-magnetic ore is not attracted by the wheel, so that we can separate them from each other. Not only this example, but it is also useful for chromite, pyrolusite ores having the magnetic property. So these are the other examples. We can have chromite, pyrolusite, in which non-magnetic impurity are siliceous impurity. The silicon impurities are non-magnetic, so that they can be separated from the magnetic part of chromite and pyrolusite. Okay, so that is the method called as concentration of ore. Various procedures in detail we were learned. Now in extraction of crude metal, how to extract the crude form of metal from the corresponding ore. For that also we are given the steps. One of the steps will be, the first step after the concentration will be roasting. Extraction of crude metal. For that, the first procedure, conversion of ores into oxides. Okay. This is possible by the procedure called roasting. What is it? Heating the ore with air mainly. So what's the significance of this? All your volatile impurities are removed easily, which means they are all separated from the ore, volatile impurities. What are called volatile impurities? The vaporizable impurities. You see the following example. If this is the example we are going to take, PBS, the lead sulfide ore on roasting. We can have PbO plus sulfur dioxide. So which is vaporizable or volatile sulfur. It is converted into the gas. So for balancing 2 times, and we are going to write 3 times. Similarly, the ZnS, zinc blend on roasting, it becomes ZnO with the liberation of sulfur dioxide volatile. And for balancing, the same idea is employed. And similarly, the cuprous sulfide, Cu2S, on roasting, it becomes Cu2O with the loss of SO2 gas. The same numbers can be used for balancing this equation also. So in all these steps, the sulfides are mainly converted into their oxides. And this is happening in the roasting procedure. Roasting is done in a suitable furnace, okay, in which the ore is heated along with air. And other volatile impurities are arsenic, phosphorus and sulfur. What is happening while roasting ore? What's happening to this arsenic, sulfur and phosphorus? That can be explained by giving the equations as follows. This is what is happening. Yes, if you take arsenic on heating with air, it becomes arsenic oxide and it gets converted into vapor like this. Likewise, the phosphorus, it's tetraatomic. On roasting, it becomes phosphorus pentoxide, P4O10. And for balancing, I can write 5. Similarly, the sulfur, octaatomic. On roasting, it becomes sulfur dioxide gas. For balancing, we can write 8 times and 8 times. Apart from that, moisture is also removed. So certain ores are roasted like this and some other ores are treated by the procedure called calcination. What is the difference in between calcination and roasting? The calcination means in the calcination procedure, the ore is heated in absence of air. This is the major difference. Without the supply of oxygen or air, the ore is to be heated. So while heating the ore without oxygen, what is happening? These things are removed. What are all the things which can be removed? The organic matter, unwanted organic matter is getting evolved and the moisture is removed. Water content can be removed. Okay. And this is the procedure applicable for the carbonate ores. So these are the carbonate ores. PbCO3, lead carbonate, that on calcination that becomes lead oxide and carbon dioxide. Likewise, the calcium carbonate, on calcination it becomes calcium oxide and carbon dioxide. The zinc carbonate, on calcination it becomes ZnO plus carbon dioxide. Just see, all these carbonates are becoming the dolomite, magnesium carbonate, calcium carbonate combination. On calcination it becomes magnesium oxide and calcium oxide. Along with that, 2 times carbon dioxide is formed. So in this particular case, apart from the carbon dioxide, water is also expelled when the ores are having some hydrate. You see, these are the hydrated form of ore, Fe2O3, which is containing 3 times H2O. The water content can be removed on heating in absence of air, so it becomes Fe2O3 solid with the liberation of water, 3 times H2O. Water is getting vaporized. Water vapors are coming out. Likewise, the bauxite Al2O3, that's going to have 3 times H2, 2 times H2O. On calcination, it becomes Al2O3 solid, and we will be having 2 times H2O. The water content present in the ore is removed in the calcination procedure. The calcination is applicable for the carbonate ore and hydrated ores, while calcination, they are converted into their own oxide with the liberation of both carbon dioxide and water. In particular, in the calcination procedure, the ores are heated in the absence of air. Air supply is not there. And after the conversion of ores into their own oxide, the next procedure must be the reduction of these oxides. The reduction of oxides are done as follows. What are all the various reduction methods? Yes, these are the various reduction procedures that we can follow. One among will be reduction of metal oxide. What is obtained above? One of the procedure is smelting. From the title we can understand separating the things by using the melting procedure. Okay, while smelting, what is happening? Sometimes the ore like Fe2O3, this oxide of iron, on treatment with carbon monoxide, that's a reducing agent used here in the smelting procedure. The carbon monoxide can take up oxygen to form carbon dioxide, and Fe is separated out. So this is what is happening in the reduction procedure. In particular, we should take 3 times carbon dioxide gas provided when you take 3 times carbon monoxide. So carbon monoxide is playing a role called reducing agent. Why this is called so reducing agent? because it is going to accept oxygen from this. Okay. In this extraction, the flux can also be used. What's the purpose of using the flux? Flux can combine with the gangue to form slag, unwanted things. For example, the limestone CaO, it is a basic flux. Along with that, we are going to take acidic gangue. See the combination. This is the basic flux, calcium oxide, and it is going to combine with acidic gangue SiO2 to form CaSiO3. The slag is formed, unwanted thing. So this is the flux and this one is gangue. The result is unwanted portion slag. In this way, the ore can be, the oxide can be reduced. Similarly, this smelting can be explained for some other substances like copper and nickel also. Smelting procedure. And a reduction by using the carbon. So in this smelting process, the carbon monoxide is playing a role called reducing agent. And reduction by using carbon. Carbon is used as a reducing agent. These are the various oxides. Zinc oxide can be reduced by using carbon so that we can have Zn plus carbon monoxide. It is in the form of solid and it's a gas. It is a solid carbon. It is also a solid mass. Likewise, Mn3O4 on reduction by using carbon, we will be getting Mn plus carbon monoxide gas. There are 4 oxygens, so that I can write 4 times, 4 times, 3 times. Equation is balanced. Cr2O3, this can also be reduced by using the carbon. So we can have Cr solid, along with that the carbon monoxide gas, 3 times, 3 times. Equation is balanced. So in all these cases, the carbon is playing a role called reducing agent. It is exclusively used for oxides like this, ZnO, manganese, and then chromium oxides. These things can be treated with the carbon in the blast furnace just by sending these ores along with the carbon atom on strong heating, which means the coke is taken in the blast furnace along with these oxides. While treating them, this is happening. Carbon monoxide is formed, which means the carbon gets oxygen from all these cases, and hence we are calling carbon as a reducing agent. This reduction process which is employed in the case of carbon. And similarly, the other will be reduction by using hydrogen. Reduction by using hydrogen. Certain metals like Fe and Eb, copper, these are all lesser electropositive than hydrogen. So in these cases, we can use hydrogen as a reducing agent. Yes, in the list we can include this also, silver. So if you take Ag2O, when it is treated with the hydrogen gas, it is in the form of solid. As the hydrogen is more electropositive, it can displace this silver, so that we can have Ag and hydrogen combined with oxygen to form H2O. And other case, Fe3O4, solid, where it is to be treated with hydrogen gas. As the hydrogen is more electropositive, it can displace this. So Fe is separated out and the water is formed along with that. In order to balance the equation, I can write 4 times, 3 times, here it is going to be 4. So the equation is balanced. Here I can write 2 times. And in these two cases, hydrogen is more electropositive than silver and iron, and hence the hydrogen is used as a reducing agent. Sometimes a mixture of reducing agent can be used. One of such case is, this is the case. You see, nickel oxide in the form of solid, that is reduced by using carbon monoxide gas and hydrogen gas. This combination is simply called as water gas. It is the reducing agent. The reducing agent can take up oxygen. When the carbon monoxide gets oxygen, it becomes carbon dioxide. When hydrogen gets oxygen, it gets converted into water, and thus it is separated, the nickel. So nickel is in the form of solid and the carbon dioxide is in the form of gas. Water is in the form of liquid. And this equation can be balanced by writing 2 times nickel oxide and 2 times Ni. It's also an example of reduction. And in certain cases, the metals can be used as a reducing agent. Even the metals can be used as a reducing agent. Okay. So how some other metals are used to reduce one particular metal? And you must know there is a procedure called as Aluminothermic process. In this Aluminothermic process, the metal like aluminothermic processing, in which the metal like Cr2O3 metallic oxide on treatment with aluminium, aluminium can accept this oxygen to form Al2O3, so that the Cr is separated out. This is a procedure called as aluminothermic process, where the role of aluminium is a reducing agent. It shows that aluminium is more electropositive than the chromium, and hence chromium oxide can be reduced by using aluminium. And it's a highly exothermic process. Larger amount of heat is liberated, and to balance this equation, I can write 2 times chromium and 2 times aluminium. So this is the procedure called as aluminothermic process. It's highly exothermic process. By heating the aluminium along with this Cr2O3. In general, for igniting this combination, some of the ignition mixers can be used up. Which is called ignition mixer. It is barium peroxide and magnesium powder. So by igniting this composite, we can combust these two Cr2O3 and aluminium in the case of aluminothermic process. Some of other active metals can also be used as a reducing agent. The best example of such cases, boron trioxide E2O3, when it is treated with Na, sodium can displace this boron so that the position of boron is occupied by that, it forms Na2O and boron is separated out. And to write the balanced form of the equation, we are writing 3 times as there are 3 oxygen. So I can write 6 times Na and 2 times boron. And other will be the rubidium oxide Rb2O3 on treatment with magnesium. Magnesium can displace this rubidium. So magnesium is forming magnesium oxide and rubidium is separated out. And in order to balance the equation 3 times, 2 times, and here we should have 3. As there are 3 oxygen, we are multiplying this by 3. And titanium oxide, that is also treated with the magnesium. So magnesium can displace this titanium to form magnesium oxide and the titanium is separated out. There are 2 times, it gets balanced. And thorium oxide, THO2, on treatment with the calcium. Calcium is the active metal which is acting as a reducing agent at a temperature of 1250 Kelvin. The thorium is formed. Along with that, the calcium oxide is smelled 3 times and 2 times. And finally, in the reduction procedure, so many reduction procedures we were seeing. The last one is auto reduction. Auto reduction. Auto reduction procedure in which we should have the best example of mercuric sulfide, Cinnabar. This ore on roasting itself is getting reduced. On treatment with oxygen, the mercury is formed and other will be the sulfur dioxide. Okay, it's a self-balanced equation. Mercury sulfide, Cinnabar is in the form of solid, it is a gas, and the mercury is in the form of liquid. Here mercury is obtained by roasting its ore, Cinnabar. So this Cinnabar itself is acting as a reducing agent, and hence this procedure is called as auto reduction. So that's the end of various reduction procedure. Then we have to learn about thermodynamic principle of metallurgy. In the thermodynamic principle of metallurgy, the main idea behind in that is the selection of reducing agent. On which basis? On the basis of delta G value of these equations. Thermodynamic principle of metallurgy. By selecting the suitable equations. You just see, it's going to be a very simple topic, how to select the proper reducing agent. That should be discussed here. You take MXOY, the metallic oxide, that gets converted into M solid plus oxygen. This is equation number 1. Here, for example, if you take 2 by Y, the metal part must have 2 into X. So 2x by Y. And the other equation, the reducing agent is carbon, means that accepts oxygen to form carbon dioxide. The reducing agent carbon on incomplete combustion, that forms carbon monoxide also. And in order to balance this equation, I can write 2 times 2 times. So this is equation number 2 and this is equation number 3. See, the metal oxide is converted into metal and oxygen by using the reducing agent as carbon. The carbon accepts oxygen to form carbon dioxide. Carbon accepts oxygen to form carbon monoxide. Now, when the carbon monoxide is accepting oxygen, you will be getting carbon dioxide. So this is equation number 4. 2 times, and here I can write 2 times. So in this combination of equations, if you take 1 and then 2, first equation and second equation are taken together, its delta G value must be negative. Delta G is negative means the process is spontaneous process that can take place by its own accord. You do not induce that procedure. Delta G value is negative for all your spontaneous process. Suppose carbon is used for this reduction procedure, you can take equation 1 and 2, and if you are getting the delta G as negative, so carbon will be the suitable reducing agent. Suppose if you take this combination, the combination of equations 1 and 3, again the delta G is negative, we can go with this idea. The carbon is taking up oxygen to form carbon monoxide in certain cases. Otherwise, if you take 1 and 4, the delta G is again negative. In place of carbon, we should use carbon monoxide as a reducing agent in order to get the delta G value as negative. So the main idea is either we are using carbon or carbon monoxide. How to select the reducing agent? And for that purpose, one of the diagram is given which is called as Ellingham diagram. We just know the diagram is Ellingham diagram. This diagram is drawn with the help of these two. Delta G naught, that is equal to minus RT ln K, which is taken in y-axis, and temperature, which is in degrees Celsius, which is taken in x-axis. We are getting various straight lines. So this is the plot. You see the temperature in x-axis. Delta G naught is taken in y-axis. and we are getting various straight lines like this. It's one of the examples. Straight line is uptime, which means for every rise in temperature, the delta G value increases. Suppose when you fix this is the 0, above 0 you can have 100, 200, below which we can have minus 100, minus 200. So it shows that at the lowest temperature, the delta G reaches negative value, which means that is spontaneous. Okay, that diagram is highly helpful to select the best reducing agent. Which reducing agent can be used? And in this particular straight line, it's a very valid point. Delta G can be calculated by using the formula delta H minus T delta S. It's a thermodynamic relationship. By using this, you can get the value of delta G. Suppose if T is equal to 0, what will happen? Delta G will become equal to delta H. So delta H is the y-axis intercept in this straight line. Y-axis intercept, delta H. And delta S is the slope value obtained for the straight line. That you should recall. And according to the Ellingham diagram is highly helpful to select the best reducing agents. Which reducing agent can be used for one particular case? Without any reducing agent, it can be decomposed like this. HGO, auto reduction process we were seeing. It gets converted into Hg plus O2. The decomposition is possible without any reducing agent. So you do not select any reducing agents for these two oxides, as these two oxides are given at the top of this particular diagram and having the decomposition temperature 600 to 700 Kelvin. And likewise, one more combination we can say, if you take aluminum and Cr2O3, aluminum is just under the Cr2O3. So the metal which is given below chromium can able to reduce this chromium. So the aluminum is just under the chromium according to this particular diagram. And aluminum can be used as a reducing agent. Okay. Any metal can reduce the oxides of other metals that are located above in the diagram. So here aluminum is located below and chromium is located above. And hence chromium oxide can be reduced as follows. You see, this is the case. If you take this particular diagram, Ellingham diagram, this is the temperature G, and here we can say delta G naught. Yes, if you see this case, aluminum plus oxygen that forms Al2O3, just above which you can find one other straight line, chromium that combines with oxygen to form Cr2O3. Here aluminum is combining with oxygen to form Al2O3. In this case, chromium that combines with oxygen to form Cr2O3. So aluminum is just below this chromium. All the metals present below this chromium can able to reduce. Here aluminum is reducing. You see that aluminum can be used for the reduction of chromic oxide to form Al2O3 plus Cr. So this is also explained based on this Elingham diagram. Okay, in this combination, the delta G is negative. For this particular equation, the delta G becomes negative. Delta G negative means the process is spontaneous process. Okay, and diagram shows that Ellingham's diagram is also giving an information that the FeO and carbon monoxide formations are intersects at the temperature of 1000 Kelvin. You just see that particular diagram. The temperature here and the delta G naught is taken at particular in 1000 Kelvin. Okay, at the 1000 Kelvin. 1000 Kelvin means these two are intersecting with each other. One will be the FeO and other one is the carbon monoxide. So in this particular intersecting point, in this particular junction, the corresponding temperature is roughly about 1000 Kelvin. Due to this reason, it indicates that FeO is more stable and CO is comparatively less stable. Okay, and hence in this particular temperature range, for the reduction of FeO, this cannot be used up. Carbon cannot be used up just below this temperature as a reducing agent. But above 1000 Kelvin, you see, above 1000 Kelvin, the carbon is lying below this one, FeO. And hence above 1000 Kelvin, not exactly at 1000, above 1000 Kelvin, FeO can be reduced by using carbon to form Fe plus carbon monoxide. It is in the form of solid. This is also a solid, and we can have solid as well as liquid, and this is gas. For balancing the equation, I can write this as follows. It is self-balanced equation, and the delta G is approximately minus 130 kilojoules per mole for this combination. It clearly shows that the delta G is negative, so the process is feasible and spontaneous. So below 1000 Kelvin, FeO cannot be reduced by using carbon, but above 1000 Kelvin, FeO can be reduced by using carbon. That's the significance of this Ellingham's diagram. Likewise, at the last part of the lesson, we are going to have various refining process. What are the various refining process? These are the refining process of metallurgical treatment. One will be the distillation, and other will be the liquefaction. And other will be the electrolytic refining. Most of the metals are refined by this particular procedure called as electrolytic refining. And we are having the zone refining. And we can have vapor phase method. By using all this procedure, we can able to refine the metal and we will be getting almost 100% purest form of metals. So this is the important matter related with the extraction of metal from the ore or treatment of ores, as well as the isolation of metal from their ore. Principle of metallurgy is thus explained. Okay, that's all.